Good morning. Myself SK SOMASUNDARAM, working as an assistant professor in the Department of Computer Science and Engineering. Today we are going to discuss about automata theory, which is a very special branch in theory of computation. Theory of computation, it deals with deep insight into the various computing devices, including a computer. Say for example, a problem is given to a computing device. This theory of computation will be able to give whether a problem can be solved in a time within this computing device, to which extent a problem can be solved, what is its time complexity, what is its space complexity, whether it can be solved in the given time, solved in the given space. Today we are going to discuss about this automata theory. So outline content of this. So we are going to discuss about a basic introduction about theory of computation, automata theory. Then we are going to discuss about what is finite automata, what are its types, deterministic finite automata and non-deterministic finite automata. Then we are going to say how this non-deterministic finite automata is equivalent to a deterministic finite automata. So first an basic introduction about theory of computations. As I said earlier, when a problem is given to you, it will able to say whether this problem can be solved within this computing devices. So it will give you the basic foundations and principles of various computing devices. It will also give you how effective a problem can be solved within this computing devices if you have provided an algorithm to this computational model. Then it has three branches. Your first branch is an automata theory, which we are going to discuss in detail now. Then the second thing is computability theory. Computability theory is nothing but it will give you an extension to the problem. That is how far a problem can be discussed, how far a problem can be solved within this computational model. Then the next branch of this theory of computation, it is computational complexity theory. What is this computational complexity theory is? It will give you the details of what is the time required for completion of this problem, what is the amount of memory, the space required to complete this problem. So this will deal with the time complexity and space complexity of any problem that is given to any computational model, for example a computer. Then what is an automata theory? So automata theory is nothing but it is a study of many computing devices. It will give you the mathematical properties of most of your computing devices. For example, they have given this. This is a finite automata which will have a different states like state 1 and state 2. You can start from state 1 and we can end in different states. We can have a transition from one state to another state based on some input symbols. Here in this example we have two states, state 1 and state 2. We have input symbols zeros and ones. So this is a finite automata, or this is a machine which will recognize a string containing even numbers of zeros. So from the starting state, on processing input symbol 0, it can move to the next state S2. From S2, on processing the input symbol 0, it can move to the final state S1. What is an automata here? Automata here is nothing but an self-acting machines. It may be a computer or it may be any computing devices. You can call that as an automata. Automata is nothing but many combinations of machines, a plural form of machine. Automaton, when you say automaton, it is only a single machine. Okay, what is the need for automata theory? Why we have to study this automata theory? Automata theory, it will give you the limits of the computations, to which extent a problem can be solved. It will give you the limits of your computation. Then you can use it for pattern matching, pattern searching in websites. Then the next one is we can design and check the behavior of digital circuits using this automata theory. This automata theory is not only applicable for computer science, you can also applicable for this electronic field such as designing of digital circuits also. Then what is finite automata? Finite automata, it is nothing but it is a very important tool for designing your hardware and software. So what is basic definition of your finite automata is, it is a state machine. State machine is nothing but it consists of many states. So what it collects is, it will comprehensively collects all the states and what are the transitions that takes place between the states on processing an input symbol. on processing a sequence of input symbols. This is what an finite automata does. What is an example of a finite automata is when a large text of a large collection of text is given, this finite automata can be able to identify a specific pattern, or if you want to identify the number of occurrences of a word, say for example a word college, this word college, how many times it occurs in a text, you can identify it in the collection of text. Then you can identify a pattern, what is a pattern that is followed in a collection of text. We can identify certain phrases, certain quotes that are available in the large collection of text. Okay, well, this is an finite automaton model. So what is this finite automaton model? It looks like this. This finite automaton model, this is a recognition of a word then. So this is an example of a finite automaton model which recognizes the word then. So we can start from the starting state, it moves to the next state on processing each and every character of the string then. So when it reads T, it goes to the next state. When it reads H, it goes to the next state. When it reads E, it goes to the next state. When it reaches N, it will reach the final state. So the word then can be identified if it is present in a large collection of text. So this is a transition on the next letter of then to the next state. Okay, what is an anatomy of finite automata? What it consists of? What is its anatomy? So we can call these as states. We have states Q0, Q1, Q2 and Q3. These are all we have to call as states. Then the state that has an arrow symbol like this, we can say that it is a starting state. Here in this case, your Q0 is your starting state. Then you have accepting states. The states which has this double circles, we can call that as an accepting states. Okay. Then what is a finite state, a finite automata acceptor? Say for example, if you are reading a string 0, 1, 1 and 1. When it reaches your starting state, you have 0, 1, 1 and 1. On reading the first input symbol 0, there is a transition from the starting state on the input symbol 0. So it remains in the same state. See here, it remains in the same state. After reading 0, it moves to it is going to read the next input symbol 1. So on input symbol 1, it goes to the next state. From the input, then from the next state, on reading the input symbol, it goes to this state. Then again, on reading an input symbol 1, it will remain in the same state. So from the starting state, if your string reaches the final state, you can say that your string is accepted. From the starting state, if you are able to reach the final state, you can say that your string is accepted by this finite automata, or a string is accepted by a computing device. Okay, what are the notations we follow in computational devices? So your notations we follow in finite automata, we have a sigma symbol. Sigma symbol, it represents alphabets. Alphabets is nothing but a set of input symbols. It may be digits, it may be characters, it may be any set of symbols you can specify there. In this case, example I have given us 0 and 1, which is used to represent only binary numbers, zeros and ones. Then you can have a string. String is nothing but sequence of your alphabet, sequence of symbols of this sigma. So if we say string is 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, all these we can have sequence of input symbols. That is what you can call it as string. Next is length of a string. How do you identify the length of the string? When you write a string as 1, 0, 1, 0, say we have 4 strings, 1, 0, 1, 0. So you can identify that we have 4 characters in the string. Then if we have a string length 0, which is indicated here in this finite automata by a special symbol called as sigma. Okay. Then we can call that as an empty string, or we can call that as a null string. Okay, the language over sigma, you can call that as an set of language over. Language over sigma is nothing but a set of string over sigma. That is a language that can be written from the set of input symbols. Say for example, you can say that a language that ends with 0, 0. Or you can say a set of string that contains consecutive ones. You can say any languages. As an example I have given you, you can have 3 consecutive zeros. Construct an finite automata for a language which has which accepts 3 consecutive zeros. Okay. Then this is a formal definition of finite automata, a formal representation of finite automata where you have 5 tuples. You can say that a finite automata can be represented as an quintuple. Quintuple is nothing but it has 5 tuples, 5 components. Any finite automata you take, it has only 5 components. The first component is capital Q. It is represented as capital Q, which means set of states. What are the set of states this finite machine or finite automata has? Say for example, you can have states A, B, C. You can have states Q0, Q1 and Q2. Formally we will represent states with this word Q, Q0, Q1 and Q2. Then the next component, component in the representation of your finite automata is sigma. Sigma represents what are the input symbols we use in this finite automata. Here for example I have given you A and B. You can have 0 and 1, X and Y, M and N. You can have any input symbols. What are all the input symbols to be used? It has to be listed in the set of alphabets. Then what is a transition function? Transition function, it is represented by a delta. Delta is, it will give you an information that from a state on an input symbol it goes to what state. How it goes to the next state, from one state to another state, if there is a transition on what symbol. This transition function will give you such details. What is your starting state? It may be Q0 or it may be Q1. You have to indicate what is the starting state, where your finite automata begins. Then you have to indicate set of final states. You can have more than one final states, so where your finite automata is going to end. Okay. Then this is an example for finite automata where you have states Q0, Q1, Q2 and Q3. Then we have represented transitions based on the input symbols zeros and ones. Say for example from Q0, you are starting from Q0 because we have a start symbol here. On reading 0 it remains in the same state Q0. Q0 on reading 1 it goes to Q1. The state that is marked with double circle, you can say that it is a final state or it is an accepting state. Q1 on reading 0 and 1 it may go to Q2. Q2 on reading 1 it remains in the same state. From Q2 on reading 0 it can go to Q3. Q3 on reading 1 it can go to Q2. Q3 on reading 0 it goes to Q0. This is an example for finite automata. It is represented here. How do you have to construct the set of states for this? So if you take this finite automata M, you have set of states Q, sigma is set of alphabets. What is the transition function? Where we have to begin the starting state, where we have to end is here F. So your Q here it is Q0, Q1, Q2 and Q3. Then what is your sigma? Sigma is set of input symbols zeros and 1. What is your starting state? It is Q0. It belongs in the set of state Q. Say here Q, this contains Q0. Then F is nothing but here I have 2 final states Q1 and Q2. This is also contained within this state, within the set of state Q. What is your transition function? Transition function is from a state on an input symbol it goes to what state. That can be indicated using a transition table like this, where we have to represent your states here, states Q0, Q1 and Q1, Q2 and Q3 on an input symbol zeros and 1. Say how to interpret this table is on a state Q0 from an input symbol 0. See here Q0 on an input symbol 0 it remains in the same state, so I represent Q0 here. Here again Q0 on 1 it goes to the next state Q1. Likewise Q1 on 0 it goes to Q2, Q1 on 1 it goes to Q2. The same thing here, Q2 on 0 it goes to Q3, Q2 on 1 it remains in the same state, so it is Q2. So then Q3 on 0 it goes to Q0, on 1 it goes to Q2. This is how you have to construct a transition table from the given transition diagram. Okay, what is a transition function? More insight into the transition function. This is for an example of finite automata. It is given like this, which has 3 states Q0, Q1 and Q2. Your starting state is Q0, which is also one final state. Okay. So when you write a transition function like this, transition function always represented with delta of q naught comma 1. That is from the state q naught on reading the input symbol 1. On reading the input symbol 1, it goes to the next state q1. This is how we have to write here transition function. Okay. Then when you take the next state q1, on reading input symbol 0, it goes to two states. If it is more than one state, you have to represent it like this. Q naught, the first state, on again 0, it goes to the next state, Q2. Okay. Then if there is no transition from a state on an input symbol, you have to indicate it with a symbol pi. That is, say for example, Q2, on reading 1, from Q2 there is no transition. So on reading 1, there is no transition, so you have to indicate it with a symbol pi. What is an extended transition function? Extended transition function is nothing but when you want to read more than one input symbol at a time from a state, we have to go for an extended transition function. As an example, this is an finite automata or a transition diagram given. Say for example, if we have to process this q naught on A. Here we have only one input symbol, so I can directly say that q naught on reading input symbol A, it goes to q1. Suppose if I have more than one input symbol to read, that is on a state q naught, if I have more than one input symbol, say for example I have given it as AA. How I get this result? Q4 and Q5. So I have to apply q naught on A. Q naught on reading A, it goes to Q1. Then again Q1 on reading the next input symbol A, it goes to Q4 and Q5. That is your result, Q4 and Q5. Okay. Then again a finite automata acceptor. How do you construct a language from a finite automata? This is a finite automata given where you have a starting state q naught, then it is also a final state. On reading input symbols 0s and 1, it remains in the same state. What is a language we are going to construct from this finite automata? What is a language is this finite automata, it will accept any string that contains 0s and 1s. You can have any combinations of 0 1, it may be 1 0 0 1 1 1 0 0 0 1 1 0 1 0. You can have any combinations of 0s and 1s. So this language, or this is a finite automata which accepts all strings of 0s and 1s. Okay. Then what does this finite automata accepts? It doesn't have any final state here, no accepting state here. It begins but no accepting state there. There is a starting state q naught, there is no accepting state. So you can say that it doesn't have any language. It doesn't accept any language. Okay, this is an finite automata. Say for example, you have a q naught and q1 two states which has an input alphabets 0s and 1s. Say from q1 on reading input symbol 1, it goes to q1. Then from q1 again on reading input symbol 1, it goes to state q naught, which is your accepting state. How do you identify the language of it? Language here it is w is nothing but string. The string represent it, you can have even number of ones. Say for example, number of ones in a given string is 2. So it starts from here, first in first one it goes to the next state. From this on reading 1, it goes to an accepting state. You can have even number of ones here starting from 2, 4, 6, 8, you can have even number of ones. Okay. Then what are the types of finite automata, which is very important to discuss here. We have two different types. One is deterministic finite automata, another one is non-deterministic finite automata. What is your deterministic finite automata is on an input symbol. When an input symbol is given, there is only one transition from the current state to the next state on an input symbol. You can say that it is a deterministic finite automata. Okay, what is your non-deterministic finite automata is when an input symbol is given to a state, there may be more than one transition to other states. That is what you can say that non-deterministic finite automata. If it is deterministic finite automata, you have one and only one state. If it is a non-deterministic finite automata, you can have more than one states. What is an example for this DFA and NFA is, if it is DFA, say you can say that you have state 0, 1 and 2. Say for example, on reading an input symbol A, it goes to the state 1. Here from 0 on reading input symbol B, it goes to the state 2. Here again on reading input symbol A from state 1 it goes to 0. Here on reading input symbol B from state 1 it goes to state 2. From state 2 on reading input symbol A and B it remains in the same state 2. So what we infer from this diagram is on an input symbol, say for example A, from the state 0 it will go to only one state, not more than one state. Say here when you take this NFA 0 on reading an input symbol A it goes to 1, and also reading an input symbol A it goes to 2, state 2. So this you can say that you can go to more than one state on a same input symbol. You can say that it is a non-deterministic finite automata. On an input symbol if it goes to one and only one state you can say that it is a deterministic finite automata. Okay, what is a non-deterministic finite automata acceptor? You have an alphabet A. We have two choices to make. Say for example, we have to proceed with either in this direction, or we have to select the second choice, we have to proceed in this direction. So if we selected the first choice, if you want to check whether this given string AA is accepted here. So this is your state machine, this is your transition diagram. So from state Q0 on reading input symbol A, it goes to the next state Q1. Then from Q1 on reading the next input symbol A, it goes to the accepting state Q2. So your string is accepted when you select the first choice. Okay, your second choice is when you select your second choice. So from Q0 on reading A, it goes to Q3. Then you have one more symbol to read, but there is no transition after this. So you can say that no transition, so your automaton hangs here. So this automata cannot be applicable to this particular set of string if you have selected your second choice. So it will reject that string if the second choice is selected. Okay, what is an observation from this? Observation is an NFA accepts a string if there is a computation of NFA that accepts this string. So every NFA, a non-deterministic finite automata, will accept a string if it has a transition diagram or a transition table that begins from the starting state and ends with the final state or accepting states on processing the sequence of input symbols. Okay. Again an example, this is an example where AA is accepted by your NFA. See here A and from state Q0 on reading input symbol A it goes to Q1. Q1 on reading input symbol A it goes to state Q2. Your string is accepted by this finite automata. What is a lambda transition, or otherwise you can call that as an epsilon transition. Lambda transition is nothing but you can make a transition without reading any input symbols. Without reading any input symbols I can make a transition. Say for example, again the same string AA, from Q0 on reading A it goes to Q1. Then from Q1 to Q2 there is an epsilon transition. That is, your read write head, this pointer will not move, but we can transit from one state to another state like this. See here your pointer doesn't move, your read head does not move here. Okay. Again from Q2 on an input symbol A, your read write head moves here, it goes to the final state, your string is accepted here. The string AA is accepted if it has an epsilon transition. Epsilon transition, you have to keep in mind that it is just used to transit from one state to another state without reading any input symbols. Okay, it may be useful in special cases. Okay, so here the language accepted L is equal to AA. This is a language accepted here. This is a finite automata which accepts this language AA. Okay, another example for a finite automata, we are going to construct a finite automata which contains the string 0, 0 and 1. So we will start with a starting state Q, then on this you take the first symbol 0, second symbol again 0, third symbol 1, 1. So from the starting state 0, if it contains, if it starts with 0, it goes to the next state Q0. Again if it has 0, if it reads 0, it goes to the next state Q00. Then if it reads 1, it goes to the final state, your string is accepted. If it is the other case, if it reads 1 from the starting state, it will remain in the same state until it reaches 0. Then here from if it reads 0, then it reads 1, once again it return back to the first state.
Okay. Then if it reads the second 0, after reading the second 0, if it once again reads 0, it will remain in this second state Q00. Then when it reads 1, it goes to the final state. Then after reading the string 001, you can say that this finite automata accepts a string that contains 001. After that, you can have any combinations of zeros and ones. Okay. Then we are going to discuss about the equivalence of equivalence of a non-deterministic finite automata and deterministic finite automata. What is its equivalences? We can say that a non-deterministic automata, if it accepts a certain languages, then there exists a deterministic finite automata which accepts the same language. For example, you take any language, say for example the previous language which contains 001. So if you construct an NFA for that language, there is an possible DFA which exists for that same language 001, for the string containing 001. So when you say there is a machine M1 which is equivalent to machine M2, that is this statement, it is represented as language of this machine should be equal to the language of this machine M2. So for example, language of M1 they have given it as 10 star. 10 star is nothing but any combinations of 1 and 0 should occur in pairs. Here again machine 2 also has the same language 1 and 0 which occur in pairs. So your machine 1 is finite non-deterministic finite automata, your machine 2 is your deterministic finite automata. So we can say this as a non-deterministic finite automata because on an input symbol Q0, on an state Q1, on an input symbol 0, it goes to Q0 as well as Q2. More than one state on a same input symbol, so this is an NFA. DFA, you can say that from a state on an input symbol, it goes to only one state. Okay. So since your language of machine 1 is equal to language of machine 2, so the language we have followed is 10 star. So 10 should occur in pairs. So we can say that machine M1 is equivalent to machine M2. This machine M1 is equivalent to machine M2. How do you say that they are equivalent? How do you construct an NFA, construct an DFA when an NFA is given or when a language is given? Okay. What is the question is whether NFAs are all equal to DFAs, whether they accept same languages. Yes, it accepts the same languages. Okay, we have to prove that a language accepted by NFA should be equal to languages accepted by DFA. How do you prove this? We have to follow certain procedure to prove that a language, if it accepts by NFA, it is accepted by this DFA. Suppose a language is given, say for example a string that ends with 01. A language is given, you have to construct an NFA for that language, then you have to convert this convert every state that is present in NFA to a state in DFA. So your DFA should have only one transition on an input symbol from a state to a next state. Okay. Finally, we have to prove that the languages accepted by NFAs is equal to the languages accepted by this DFA. So when a problem is given like this, construct an NFA for the following language. A language given us a set of string which ends with 0 and 1. After converting an NFA of this given language, we have to convert this NFA into a DFA. So how to begin with our solution is, so we have to construct an NFA for this. How to construct an NFA for this language L? So we have to construct a transition diagram like this, where we have to begin with the starting state, then we move to the next state Q1 on reading a first symbol 0, then it goes to the next state Q2, which you can assume it to be a final state, then it from Q1 on input symbol 1 it goes to the state Q2. From Q0 there may be any combinations of zeros and ones. So this is an NFA which is constructed for this given language. So where we have 0, where we have a string, where we have an input symbol 0 and an input symbol 1. This is a finite automata which ends with an input symbols or set of input symbols zeros and 1s. Before this zeros and 1, you can have any combinations of 1s and zeros. Say for example, you can write 0 1 1 0, 0 1 0 1. You can write 1 1 0 1. You can write 0 0 0 1. Say for example, if you take this string, it is 0 and 1. 0 and 1, it remains in the same state. Then on reading this 0, it goes to the next state. Reading on this 1, it goes to the next state. When you take this string, reading 1 and 1, it remains in the same state. Reading 0 to the next state, reading 1 to the final state. So this string is also accepted. When you take this next string, reading first to 2 zeros, it remains in the first state. On reading the next 0, it goes to the next state. On reading the 1, it goes to the next state. Okay, so how to convert this constructed NFA into an DFA? For this, we have to construct an transition table for this NFA. How do you construct a transition table, which we have already discussed? We have to write what are the states available. We have states Q0, Q1 and state Q2. Starting state is indicated by an arrow mark like this. Your final state is Q2, which is indicated by an asterisk like this. On reading, an input symbol 0 and the input symbol 1. So Q0 on reading input symbol 0, Q0 on reading input symbol 0, it goes to the states Q0 on reading input symbol, again Q0, and also to the next state Q1. Then again Q0 on reading input symbol 1, it remains in the same state Q0. Then Q1 on reading input symbol 0, there is no transition, so which is indicated by a symbol pi. Q1 on reading input symbol 1, it goes to the next state Q2. From Q2, there is no transitions on 0, no transition on 1. This is a transition table for this constructor NFA. Then if you want to construct a DFA from this NFA. How do you construct a DFA from this NFA? We have to write what are all the states that are available in this NFA. What is the equivalent in DFA? So when you take the set of states Q, here set of states is you have states Q0, Q1 and Q2. In DFA, so far we doesn't know what are the set of states, we have to identify this. What is the set of alphabets used here? Set of alphabets used here, it is 0 and 1. We are going to use the same set of alphabets here, 0 and 1. The transition function for this NFA, you will represent it as delta n, which is nothing but your transition function of NFA. Then here it is delta d, which is a transition function for DFA. Okay. Then we have to represent the starting state. Starting state here it is Q0. We will assume the starting state of DFA is also Q0. When you write states in DFA, you have to represent it in square brackets like this. The starting state I will indicate it with a symbol that it represents A. Then what is the final state here? Final state of this DFA, you have Q2. Q2 is the final state here. Here final state, so far we have not constructed DFA, so your final state is unknown here. How do you identify your final state of your DFA is the states that contains this final state of NFA Q2. You can say that all those states will be the final state of your DFA. Okay. So how do you construct this DFA? So you have to follow the steps that step number 1 is you have to start from your starting state of this DFA. Starting state of this DFA, it is represented as A. A on an input symbol 0. You apply your transition function for the NFA. Transition function for NFA, it is delta n. Delta n is equal to A is nothing but Q0 on input symbol 0. It goes to the you identify its transition table or a transition diagram. Q0 on reading input symbol 0, it goes to states Q0 and Q1. What is the transition function for the DFA? Delta D, you represent the starting state in brackets Q0 on reading input symbol 0. You exactly change this to square brackets. This is a new state in your DFA, you represent it as B. Then again A, on input symbol, next is input symbol 1. What is your delta N? Delta N Q0 on reading input symbol 1, it goes to Q0 on reading input symbol 1, it goes to Q0. Then delta D Q0 on input symbol 1, it goes to the state Q0, which is an already existing state. So mark it with the same symbol A. Your next step is you have to select your next state. What is your next state is you have state Q0 and Q1, which is B. B on 0. So what is delta N? Delta N Q0 Q1 on input symbol 0. It gives, say you have more than one state here, one symbol to process. So what you do here, you take a union of this states, that is delta N of Q0 on 0 union delta N of Q1 on 0. So what is Q0 on 0? You take from the transition table Q0 on 0, it goes to Q0 Q1 union Q1 on 0. Q1 on 0 you have pi. Anything that is union with pi, you will get the same states. So you will have Q0 and Q1. What is your delta D? Transition function for your DFA. You write the same in Q0 Q1 on input symbol 0. It gives you Q0 comma Q1, which is an already existing state. So it is B. Then again B on 1. B on 1 transition function for NFA. You have Q0 Q1 on reading input symbol 1. Transition function, if there is more than one state, you have to take union Q0 on 1 union transition function for NFA Q1 on 1. So Q0 on 1, you check from the transition table, Q0 on 1 it goes to Q0, Q1 on 1 it goes to Q2. So you have new state Q0 and Q2. You write it in the form of a DFA, state of a DFA, that is Q0 Q1 square bracket on 1 it goes to a new state Q0 and Q2, which is a new state, we indicate it as C. Then we have to write it as, we have to start with the next state here. Yeah, step number 3. Step number 3 is you have C on input symbol 0. What is your C is? Transition function Q0 Q2 on 0, it goes to, when it has more than one state, you again take union, which is delta N, then again Q2 on 0. What is Q0 on 0? It goes to Q0 Q1 union Q2 0, it is pi. So you get the result as Q0 Q1. So when you write it for the transition function of DFA, you have Q0 Q2 on 0, it goes to Q0 and Q2, which is an already existing state C. Okay. Then the next one is C on 1. The next set of state on an input symbol 1. What is delta N? Delta N of Q0 comma Q2 on reading input symbol 1. So you have delta N, split it or find a union of this, union delta N Q2 on 1. So Q0 on 1 it goes to Q0 union Q2 on 1 it is pi. So you get Q0 here. So you write it for the DFA transition function of DFA Q0, then Q2 on input symbol 1, it goes to again an existing state. Q naught, it is nothing but a state, first state, which is A. Now you have no more new states to process. We have state A, which is nothing but Q naught. We have state B, next state B, which is Q naught, Q1. State C, which is nothing but Q naught, Q2. No more new states to process. So out of this, you have to construct a transition table, this time for DFA. What is a transition table for this DFA? You have to construct a transition table for DFA. So what is your set of states here? You have states Q naught, which is your starting state, so arrow symbol here. Your next state is Q naught, Q1. Then your next state is Q naught, Q2. This Q2 is a final state in NFA, so this state has to be a final state in DFA also. The states that contains this Q2, which is a final state in NFA, will be the final state in DFA. What are your input symbols? You have input symbols zeros and 1. Q naught, that is your A, on input symbol 0 it goes to Q naught, comma Q1. Q naught on input symbol 1 it goes to Q naught. Then Q naught, Q1 on input symbol 0 it goes to Q naught, comma Q1. Then on input symbol 1 it goes to the new state Q naught, Q2. Q naught, Q2 on 0 it goes to Q naught, Q1. Then Q naught, Q2 on 1 it goes to Q naught. This is a transition table we have constructed for the DFA. For this you have to once again construct a transition diagram. Transition diagram for DFA, where you have to represent the states. So your Q naught, which is your starting state. Then you have a next state, which you can say that it is Q naught, Q1, the next state. Then the next state we say that Q naught, Q2, which is an accepting state, so you represent it with a double circle here. So starting state from Q naught on input symbol 0 it goes to the next state. On input symbol 1 it remains in the same state. On input symbol 1 it remains in the same state. So then Q naught, Q1 on input symbol 0 it remains in the same state. Q naught, Q1 on input symbol 1 it goes to the next state. Then from Q naught, Q2 on input symbol 0 it goes to the previous state 0. Then Q naught, Q2 on input symbol 1 it goes to Q naught on input symbol 1. This is your transition diagram for this DFA. So from a language we have constructed an NFA, we have converted that NFA into this DFA. Finally we have to conclude that if a language L, if it is accepted by NFA, then there is a DFA that accepts this. Yeah. So we have to conclude the statement that if there is a language that is accepted by an NFA, then this NFA can be converted to DFA, which also accepts the same language L here. Okay, thank you.